Yeah, good morning, everybody. Um, so I received your midterm submissions and I started grading them. So hopefully by next week I will finish it. Well, I graded the first problem and almost all answers were correct. And I didn't expect other results because you did this poll, so you had more time to think about it. So this week we start and finish another topic, which is unsupervised learning. So we will cover several algorithms and just a little bit fun story about the first algorithm. When I had interview for the position at RIT, they asked me to explain k-means algorithm, which is the first in our list. And when they gave me the curriculum of the machine learning class, there was no unsupervised learning at all. So I had to change the curriculum for my class. And I was thinking that if they asked for this algorithm, I should also teach this algorithm when they hired me on the position to teach machine learning. So that's why the previous part of the course was pretty dense because I had to compress the material to cover a lot of things. Okay, so we will talk about k-means, k-medoids, dbscan, hierarchical clustering, and Gaussian mixture clustering, which is probabilistic algorithm. And maybe we will talk about self-supervised learning when we create, for example, embeddings for words from texts without any supervision. So the first idea for what is the difference between supervised and unsupervised learning? For supervised learning, we have features X and targets Y. For unsupervised learning, we have just only features X. We don't have features, we don't have targets. And there are some examples when we want to use unsupervised learning. One task is clustering, another anomaly detection. In documents, it's topic modeling. In dimensionality reduction, it's visualization. If we have multidimensional data and we want to map them into low dimension, like 2-dimensional features. And some others like empating. So here's example. We have a bunch of images of the faces, and we want to group these images such that each group corresponds to one person. And you can see here that, for example, in cluster 13, we have grouped an image with another person. Ideally, we want to have just images of the same person in each cluster. But we don't have labels on these images. I mean, we have labels in training data, but in real life, we just have a bunch of images and we want to group them into clusters. Prediction of the next position of the pedestrian. So the main differences between supervised and unsupervised learning is that in supervised learning we have the loss function, which minimizes our errors. In clustering, our goal is not well stated. Like in images, we just want to groups, but what are the criteria for grouping these images? Yeah, then also we have true labels in supervised learning. In case of clustering, we even don't know the number of clusters that we want to get in the result. And different quality metrics are used. So let's start with the first algorithm. K means. So let's assume we have some data points, and in case of classification, I used crosses and zeros or boxes for different classes. Here we don't have actually different labels. So every point will be just a circle. So we have just a bunch of points on the plane. And our goal is to group these dots in, let's say, two clusters, in two groups. So the first step is the zero step, is to define the number of clusters, because it's not given in advance, and we should start with just setting the number of classes explicitly. Let's say I want to set this as 2. The next step is to find the centers of these clusters. It's called they are called centroids. Centroids. So typically, you can just choose 2 arbitrary points from your data. Of course, you can take points that do not belong to your data sets with some arbitrary coordinates, but it's easier to take just randomly 2 points from your data. So we define centroids for the first class. Let's see which index I want to use. Let's use lowercase, and centroid for the second class. And if we are lucky, we will get these points reasonably well, but we could also get 2 neighbor points as our initial centroids. Then the next step is to assign every point in our data set to each class. And how to do this? We will calculate the distance between every point to the centroid 1 and to the centroid 2. And we assign a point xi to class 1 or class 2 by a smaller distance. So um, we assign, for example, we calculate the distance from this point to centroid 1, the distance to centroid 2, and we assign then this point to class to the, if it was class 1, to class 1. And we perform this for every point. So this is the second step. We will classify every point as belonging to cluster 1 or cluster 2. After we calculated the, well, in this case, I think it's clear that these points, 4 points, will be classified as cluster 1. These 2 points will be classified as cluster 2. Bless you. The next step, after we assign points to each cluster, we will recalculate the centroid position because it was arbitrary choice, and how to improve the centroid position. So if we have points in one cluster, let's say in this cluster, the new centroid, so it follows from the name of algorithm, will be chosen so as the mean of the coordinates of each points in this cluster. So we have coordinates x1, x2. Okay, I used lowercase, maybe x and y. Let's use, because we don't have targets, I can use just coordinates as x and y. And calculate the mean of the first component and the mean for the second component in our cluster 1. And the mean of this, I don't know where it will be, maybe here somewhere. So the mean of the components of all points in our cluster will represent the new centroid. So the first step is to recalculate, update centroids. Centroid, okay, without indexes, it will be the average of the component of the coordinates of points from each cluster. And after that, we should reassign the points, because now the distances from each point to the new centroid are changed. We will reassign, so iterate. Reassign the points to clusters, to new centroids, recalculate centroids, and repeat until we won't change the distribution of points. So this is the algorithm. If you calculate instead of average the median of the components, then you will get another algorithm, which is called k-midweights. So k-midweights is the same algorithm, but instead of using centroid as mean, we use centroid as median of the first coordinate and oops, and the second coordinate. Okay, so we covered two algorithms now for clustering. Now let's look at the implementation. We prepared a whole notebook for these clustering algorithms. One second. I have the link. So yeah, let's look at these k-means. So we have these data points, and we first set the centroids. For example, I can set centroid here and centroid here. So every point is classified based on the distance to the centroids. I mean, every point on. So do you remember what was the first step? Well, the first step was centroids. The second step to calculate the distances from every point to the centroid and reassign the points, the clusters of these points. So let's just take a quick look. So maybe I don't know. It's hard to say which point will be assigned to blue. Let's just run. Okay, so this is the reassignment of the points to centroids. What was the next step? Recalculate centroids. So because we use the average, where we'll move our blue point? Somewhere to the left. And the red point also should move a little bit to the left because we have some points here. So update centroids. Next step, reassign the points to clusters. So yeah, definitely these points now will be assigned to blue cluster. The next step is to update the centroids. I think the red dot will move inside this red cluster now. Now we reassign the points and nothing will change because it looks like the good assignment. And because nothing was changed, the centroids also won't be updated. And this is the end of algorithm. But if I would, it depends how I choose the points. If I choose, for example, points here and here, then I will get a different classification because now these points should be assigned to the first cluster, I believe. Yep. And when we update centroids, we will get this picture. And yeah, and we will get a different clusterization. Now let's run my code. So here is data set. Here is data. So I should mention where I took this data. So there is a recommended textbook for our class. I believe. Oh no, it's not this one. Um, okay, it's here. The hands-on machine learning, something like that. With scikit-learn, I believe. So I don't use these textbooks for assignments or reading, but this textbook has nice GitHub with illustrations and code for every topic. And I used illustration for some illustrations from this textbook. So for example, they have also k-means, and I use the data set from this textbook. So it has a lot of examples. So maybe for your reference, you can use this textbook sometime. For example, for time series prediction, they have a chapter on that. Okay. So I use the data set from that textbook. And the first step, I initialize clusters. Initialize the number of clusters, 5. And because just by observation, we want to have maybe 5 clusters here. And choose randomly 5 points. So sample. And then let's run maybe one step. Let's see. Okay, let's run 10 steps. It's updating. Okay. So as you can see, the the first choice of clusters wasn't pretty good, and maybe we would expect to see this points as different clusters, but instead we split it this set of points. Let's try another initialization. Oh, this initialization is better. And yeah, now we get the good separation. In implementation of these algorithms, they use multiple starts, multiple choices of their initial centroids, and then choose the best. And how to choose the best? We should use a metric. And the metric which is used here is called inertia. What it does, it calculates the distances between, for one class, it calculates the distances between points in this class and centroid of this class. And take, for example, squared distances. Then calculates the distances between points and centroid for another cluster. I'm saying class, but we talk about clustering. And sums up these square distances, and this metric is called inertia. So, here is the decision boundary. Let's plot decision boundary. So we can run a for loop, as I did here, a for k in range between 1 and 10, so 1 and 9. And this is the sum of square differences between points and centroids. So we run our algorithm for one cluster, for two clusters, for 4 clusters, for 5 clusters, and you can guess if we use the number of clusters the same as number of points, we will get 0, because the distance will be 0 between points and centroids. But which number of clusters to choose? This is called elbow rule. So the point where the change of our quality metric, in this case inertia, has the most drastic change. And using this metric, we should use 4 clusters. What do you think? Is it correct number of clusters for our data set? Close to 5. We want, yeah. So this is the standard metric. There is another metric for clusterization, which is called silhouette. Let me open the definition. So this metric is the visualization, and it's calculated based on 2 numbers, A and B. A. For each cluster, we can calculate the distances inside this cluster. So if I can call this inter-cluster distances, but there's inter-cluster metric is a little bit different from this, which is used for nearest means. So we calculate the average of distances, because we also divide by the number of class points in our cluster I minus 1. It's the same as 1 over n minus 1 or 1 over n. So the average distances inside each cluster. Then we calculate another number. The distances from points in cluster I to the points in another cluster, in cluster J. So B is the distance, sum of the average sum of distances from points in one cluster to the points in different clusters. And then the silhouette metric is defined as this fraction. The difference between distance to the points of other clusters minus distance inside our cluster. And also normalized by maximum between A and B. So this normalization we'll just keep this number between -1 and 1. Um, so if our clustering is bad and the distances to other clusters are smaller, so the points in other cluster are smaller, then this metric will be negative because B will be smaller than A. If our clustering is good, then the distances inside cluster A should be much smaller than distances to points in other cluster, and our numerator should be large. So let's plot this metric in our case. Mhm. So these are silhouettes for number of clusters 3, 4, 5, and 6. The length of these shapes represent this S metric. The width represents the number of points in this class. It's kind of the balance. So looking at this for plots, what do you think? Which metric, which K is better? 3, 4, 5, or 6? What do you think? For example, for 3, this second cluster has pretty small length, small value. Yes.
I think it's under 4 or 6. I'll go with 4.
Yes. So if you look at the cluster number of clusters 4, they have pretty similar silhouette metric, but the balance is not pretty good because the second cluster is much wider, has much more points than other clusters. So yes, maybe 4, maybe 5, maybe 6. Yeah. So this is another metric that we can use for clustering. Okay, so I hope you understand this algorithm. Now let's talk about the other one, dbscan. D stands for density. I don't remember other names. So it's kind of density estimation of the data. And this algorithm uses two parameters, two hyperparameters. One parameter is epsilon. Epsilon is the radius of these circles. Um, and the second parameter um, if I remember, it's the number of points inside one circle. Let me double check. dbscan. Yes, the other parameter, minimum number of points to create a separate class. For example, this point n, it doesn't have points inside this circle, and we won't assign a cluster to this point. It will be just no, n stands for noise. But if we have, for example, one or it, so this is the hyperparameter. In this case, 4 points in one cluster, then we will create a cluster. And there is also point B, which stands for boundary point. Um, let's see. Because they contain one point of another point from our data set, but not the minimum number of points, not the 4 points. So let's look at this algorithm. So we can set these parameters, epsilon and the number of points, and start. So it goes point by point, plots the circle around the point of the radius epsilon, and looks at the how many points other points fall in this neighborhood. If the number of points is greater than or equal to this minimum number of points, it will assign the same class. If the number of points in the neighborhood is smaller, it will start the new cluster. So for example, if we choose epsilon small, um, well, this is the number of points. If we choose epsilon small, then we will get more clusters because in a small neighborhood, we will have now less points than in previous case. I don't want to wait until it finishes the clusterization. Okay, let's apply this algorithm to our data. With different parameters of epsilon and the minimum number of samples. So I increase epsilon 0.1, 0.2, 0.5. And in the first row, I'm using 2 neighbors in neighborhoods, then 5 neighbors, then 10. And you can see the different results of clustering. And we don't have any actually good clusterization because these 2 clusters are always glued together. Okay, let's see. If it's still running. Okay, so this is the second, well, actually the third, because we used also k-mido, it's the third algorithm. The next group of algorithms is called hierarchical clustering. Hierarchical clustering. And they have two subgroups, agglomerative and divisive clustering. And we will use the very popular data set in machine learning, iris, Fisher iris. So it's popular because it has just a small number of features. Iris data set. And it's pretty old. So it has three, I believe, or four different types, species of irises. And they measured the length of petals and something else. I don't remember. And here it is. Yeah, three types of flowers. And they have four features. I don't remember which feature. Okay, it represents. I remember maybe one feature represents color, another length of petals, and something like that. So you will see this data set, I believe, in every textbook on machine learning. So let's apply hierarchical clustering to this iris data set. It's also built in inside. Oh, actually, okay. So how hierarchical clustering works? Um, I assigned 5 clusters. Let's see. Yes, I assigned 5 clusters. So that's why we have labels from 0 to 4. So first, it depends on the approach, agglomerative or divisive. In divisive clustering, we first create one cluster. All the points will be in one cluster. Then we will split these points. So in this image, you can think about like this upper level when we by all points as one cluster, then we split into two subgroups into. So this is called divisive clustering. Agglomerative clustering is different. First, we create cluster for each point, like here. So we have cluster, these 3 points clustered, these 4 points clustered, these 3 points clustered. So we create a small clusters, and then we combine these clusters based on the distances between, for example, let's look at maybe these two clusters, green and red. We can calculate the distances from every point in our green cluster to points in orange, in red, in purple, and so on. And based on the smaller distance, we will combine clusters when the distances between points in these clusters are smaller. So this is how we agglomerated clustering, combine these clusters in one cluster. So we start from small clusters, and then we increase the size of these clusters. So, for example, I know that we have just three types of flowers. So how to get three clusters from this picture? Let's see. So this is two clusters. Okay, so we should draw a line like here. And now we have cluster 1, cluster 2, and cluster 3. So this is called hierarchical clustering. If you want to cluster in 4 groups, then you should draw a line lower and so on. Okay, and here I applied this hierarchical clustering for our data, and you can see that it clusters pretty well our data. Well, spectral clustering is another hierarchical clustering. Let's skip that. So here's a fun just illustration. I apply clustering for image, and the image has different colors. I cluster these colors into just 3 groups, and then should upload the image. And then when I cluster these colors just in 3 groups, this is the image with 3 colors. So I used k-means. It means that I used the average color for each group. So here you can see the 3 colors. Something close to green, something close to black, and something close to beige. And well, of course, nobody uses that, but you can think about this as dimensionality reduction. Instead of keeping 258 colors, you can represent the image with 3 colors. Okay, the last clusterization algorithm is a probabilistic algorithm. It's based on Gaussian mixture. So let's look a little bit at the illustration. There is a theorem that you can represent arbitrary distribution as the sum of Gaussian distributions. There is another theorem that we will talk about when we will talk about neural networks, that arbitrary distribution you can represent as arbitrary function you can represent as the sum of sigmoids. That's why sigmoid function is also popular. So you can see here kind of different groups of points, and we can represent this group with one Gaussian, with one bell curve. So this is the estimated distribution, but we can fit, in this case, I fit 3 Gaussians, yellow, green, and blue. And the sum of these three Gaussians with some coefficients phi are some constant, will actually fit very well our original distribution. So how to use now this is for clustering. Here's the algorithm. We take arbitrary point x, calculate probability for yellow Gaussian. Calculate the probability for yellow Gaussian, this probability will be high. Calculate the probability for blue Gaussian. For blue Gaussian, this probability will be low. And calculate the probability to belong to green Gaussian. For green Gaussian, it will be also very low. And we choose the class or the Gaussian by the highest value of the probability density. And this is how these points were labeled based on the mixture of Gaussians. Let's see if I have other images. No. Okay, let's look at the code. So I feed 5 Gaussians here. And yeah, this is the result of clustering. So if we plot level curves, you will see these kind of level curves of our probability density function. It's two-dimensional. So the height of PDF is the third dimension. So this is kind of the viewpoint from above. Let's see if I have the three-dimensional plot. No, I don't have three-dimensional plot. So yes, and then you can classify the points based on the probability density. For example, for this point, this Gaussian will have high probability density comparing with other Gaussians, and we will classify these points as belonging to this Gaussian, the component, and so on. And there are some metrics. We can calculate the likelihood because it's the probability. We can calculate the likelihood and choose the best number of Gaussians based on this smaller value of the likelihood. As you remember, likelihood is the log likelihood is the log of joint probability. And yeah, it looks like 4, 5, 6, 7. All these numbers result in the good clusterization. There are other parameters, Akiyaki information criterion, which is likelihood plus some regularization term. Okay. Yeah, that's it about clustering. We have k-means, k-midoids, dbscan based on the density, hierarchical clustering, and the probabilistic approach Gaussian mixture. Let's talk about now self-supervised learning. So this was unsupervised learning. Let's talk about self-supervised learning. So what if you want to build a recommendation system? Or, for example, let's see if I have this example. Yeah, which is called collaborative filtering. You can create, so you have a matrix of users and their rankings of movies, for example. I is the I, stands for item, and U stands for user. Let's say user watched movie with index 1, 3, and 4, and we have some metrics, maybe the time of watching or some ranking. Then we have user 2 with who watch different movies and so on. And we want to recommend a new video to each user. So for example, user 1 watched videos with movies with indices 1, 3, and 4. So maybe we shouldn't recommend this video. For example, in YouTube recommendations, I get recommendations of my recorded lectures uploaded. Do I want to watch my lecture? Maybe sometimes to refresh before next class, but so we want to recommend a new video. But how to recommend a new video if we don't have actually the preferences? So the idea here is to create for item and for user, create a vector with some parameters. Okay, I used lower. That's why I'm using uppercase index, because now I want to use multiple features, and I can't write I1, I2 because I1 stands for the user. Let's use maybe X1, X2, and so on. So we will create a vector with unknown numbers. So X1, X2, and so on are hyperparameters. Let's say for user 1, so we will use also upper script 1. Oh, sorry, for item 1. And for user, for example, for user 1, we will create vector of the same size with some numbers y1, y2, yd. So these vectors are called embeddings of items and embeddings of users. And again, for each user, its own vector. So in the end, we will have d times the number of items, unknown parameters, plus d times the number of users, unknown parameters. So a lot of parameters. And we want to learn these parameters. How to learn these parameters? We can create the dot product. For example, here we can take a dot product between user 1 and item 1. because now user and item are vectors, so we can create a dot product and create a loss function. A loss function will be so again, we don't have any labels. We have just data and we learn from data. That's why it's called self-supervised learning. In loss function, we will calculate, for example, so this dot product is called also similarity. For example, user dot product between user one, I will use just dot times item one minus 5 squared plus we know the preferences of the first user for item 3. So I will skip item 2 and will use only known preferences. So user 1 times item 3 minus 4 squared and so on. So I will use as loss function so what I want to approximate? I want to approximate the preferences of my users, known preferences. And this is how every u and every I contains also the numbers. So then I will take a derivative with respect to x1 superscript 1 with respect to x2 superscript 1 and so on. And this is how I will actually learn these embeddings. After I learned these embeddings, I can calculate the preferences of user 1 with item 2. Because I will get the embedding for item 2 from other users. And this is how I can predict the preference of user 1 for item 2. And then you calculate these preferences for all items, rank this preference, maybe remove the watched movies, and returns as a recommendation. So this is the simplest. Yes.
So this is the loss function with respect to user 1 for all items.
Yeah, but it also will be for you plus user 2. So the loss function will contain the same number of terms as the number of known preferences in our table. Yes. So the idea is that our loss function should contain all these unknown parameters, these embeddings. For all items and for all users, we won't have for all so hopefully we will get the terms with all u and with all i's, but it doesn't mean that we should have the terms for all combinations of user 1 and all items. It's fine if we will have combination of user 3 and item 2, but it also will allow us to learn the embedding for item 3. Well, I think the simplest explanation is that the number of terms is the same as the number of known rankings. Okay, so and this is also called matrix factorization. So the other example of when we use matrix factorization is, well, it was used before large language models, because now we can just ask large language model to return to classify which topic belongs to our text. So but before that we used as you remember, we had documents and we had counts of words, how many times the word I was in this document, used, how many times the word some other word was used. So we create counts of words in different documents, and then we can represent our matrix, which has the size of number of documents times the size of dictionary number of words, as the product of two matrices. To get the same shape, the number of documents times the number of words, we should have the first matrix with the number of rows the same as the number of rows here, and the second matrix with the number of columns the same as the number of columns in our original matrix. But the second dimension can be arbitrary, and the second dimension will represent actually the number of topics. In this case, when we multiply these matrices, this is exactly the same as taking the dot product between row and column. So the same idea. So to find these two matrices, so these are matrices with unknown parameters. So that's why we denote these parameters by phi and theta, and we should learn these parameters. How we will learn these parameters? In this case, we have all the data. In collaborative filtering, we have some missing values. In this case, this matrix is complete. So we will just take the, for example, first row by first column and minus the element with indexes 1, 1 squared, and so on. So this will be our loss function, and we will learn these two matrices, and we can interpret these inner dimension as the number of topics, and classify. So, for example, cluster our data into T topics, and then take one document from this cluster and assign the topic to this cluster. Then take one document from another cluster, and if you consider that, for example, it's medical, then you can assign this topic to the entire cluster. So, what else? Dimensionality reduction. The other application of unsupervised learning is dimensionality reduction. But maybe if you're interested about word embeddings, there is also another application which is called back of words. Word2Vec. Again, it was used before large language models. When we represent every word with some embedding, and in other words, you can represent a word with a vector, and then you can plot these word embeddings, and it's interesting that these words, they will be grouped by some similarity. For example, here it's Spanish, I believe. Huge, big. So in language modeling, we can use the same idea to learn representation of words. Like we learned representation of users, items, we can learn representation of words based on a lot of texts. And it's interesting that these embeddings will group in some meaningful clusters. So if you're interested in this topic, on my GitHub, there is a course, large language models. So you can find a lot of information here about word embeddings, large language models, GPT, BERT, and so on. So maybe you will have time during summer to learn about large language models. There are also recorded videos, so you can watch, and if you want, you can do homeworks. Okay, so I have one. The dimensionality reduction. I believe you've heard in different courses, PCA, principal component analysis. When we, for example, here I have three-dimensional cross, then I project this into 2 dimensions such that it preserves the shape. And the most popular method is called, so this is visualization of images of digits, handwritten digits, mixed with PCA. The more popular method is called TSNE, and you can see the difference here. Like digits are don't have good separation. With another method, T distribution neighbors estimation returns a better result, but I won't cover this method. You can read about this in lecture notes, and also it's covered in large language models class in the second lecture. Okay, so let's finish our brief overview of unsupervised learning. And next week we will start deep learning.